Good afternoon, this is Schweitzer, and we're looking at setting up a little smart notes on acids and nomenclature of acids. You'll find that in this particular chapter, this is a chapter on reactions, and we're going to be using, obviously, acids in acids. So we want to know a couple things about them and feel comfortable using them when we're ready to go here. So anyways, how do I give acids a name, and can I recognize one when I see one? That's our overall goal here. Acids have a name, they have a formula, they have a structure. Let's start with just recognizing one. So first of all, acids have an H out front. We call this a hydronium ion. Hydrogen, might be even another way you just say it, hydrogen. It is an H+. It's sort of kind of like a cation. Like an ionic compound, and this would be an anion like this. That doesn't need to be necessarily -1, just negative. You can have multiple charges. So we're looking at a situation where we have just any anion hooked up with an H on front. So that's in front like that. This would be our anion. Okay, and although not like written in stone, like people kind of get away from it a little bit, but in water, this means aqueous. So technically, for the acids that we use, they would want to be in acid. For example, HCl in water technically would be hydrochloric acid. But HCl not in water, let's say maybe as a gas, would be hydrogen chloride. I would say that for the most part, we will just stick with this. And in our class here, even if for some reason myself or a different teacher forgets to put this on here, we're pretty much meaning that this is an acid. And on a test, unless it's a solubility type reaction, one where we're specifically talking about this, then you wouldn't be downgraded for that. But so we wouldn't downgrade you specifically for writing an acid without the aqueous. There might be other reasons why the aqueous might need to be there, but not because it's an acid. Okay. All right, so we can recognize one when you see one. So of these guys, which of these guys are acids? Okay, pause the video for a second. All right, so this is water, typically not considered an acid. Okay. Although it has an H and ion, so someone might consider it an acid. Someone might call it hydroxyic acid or oxic acid. It's but typically just thought of being water. Okay, it does play a very critical role in acids. Obviously, dissolving in water is critical, but in itself, we don't typically call it or recognize it as being an acid. So, although there's more to that story than just that, but typically no. This one, yes. Okay, it's called hydrofluoric acid. This has H's, but because the H's are not out front, we wouldn't maybe recognize this, and it's just not acidic. Okay. This guy right here is, yes, again, we did leave off the aqueous on here, but you know, okay. Another example I might have on here would be like, say, NH4+. Okay, now this guy actually is acidic. So you say, well, hold on a second. I thought that H is going to be out front here like that. And that is just an exception here. This is ammonium, and ammonium has literally been around forever. So it's got a little way in which we do things with it a little bit differently. But it's very common, and people just start to get recognized. Oh yeah, that's a weak acid. Okay. All right, so let's jump on to a couple things here. So types of acids. So there are basically a couple types of reactions that we can use, and we'll learn about these reactions in class as we go through this chapter. But there are a couple different types, and one of them would be just called like a solubility reaction. Okay, we'll learn about that in this chapter. We're going to learn about redox reactions in this chapter. And there's also an acid-base reaction, which is going to be held off for the actual acid-base chapter. So we're going to use these two reactions in this particular chapter. And just so we know that oxyacids have the ability to also undergo redox reactions. And oxidation reduction reactions, you might think of things like fire or burning things. So that's why we label them oxyacids, because they have more of an opportunity to do things like those nature of those reactions. So they have a special way which we name these. And it's not too hard to recognize an oxyacid when you see one, because literally it contains oxygen. All right. Now, when I look at this guy, a couple things I'll point out. We have H, all right, out front, and then X follows that template. And X is typically a polyatomic ion. Okay, we have a sheet of these things that we list, that we use, and you just want to be able to go on there and look at them. Okay, but now again, keep in mind, there's very few of them actually that the many atomed ions that don't contain oxygen. Okay, one of them is hchem. Now this one here is a non-oxy acid, so we'll highlight that one right now in a moment here. Okay, so types of acids, we have oxy acids, we have non-oxy acids, and in this case, just this guy here is going to be an oxy acid. So like one we might highlight here would be HNO2 and HNO3. These guys are both oxy acids. They contain oxygen. This guy is using the anion of nitrite. And this one is using the anion of nitrate. And this one's using the anion of cyanide. Okay. So in cyanide, again, no oxygen present. Ite and ate, okay, lots of times kids realize that, okay, that 8 means that there is one more oxygen than the ite, right? But in this case, what people sometimes neglect to even think about is that it means it contains oxygen. Okay, it's OX. Okay, so in that case, if you see something that's ionate, then you should be aware of the fact that, okay, yeah, this thing contains oxygen, and it's going to be an oxyacid. Okay, if you see something like ending in "ide," then you realize, oh, there's no oxygen present, so I'm going to use the non-oxy rules. Okay. All right, so now once you figure out what type of acid it is, we're going to just follow some certain rules for how we do this. Okay. So these rules are simple things, and once you start using them, you won't even really think about it. But until then, good note card material. Okay, so let's try an example here. I'll put the answers here, but I'm going to put my work over here. So first of all, this guy here is going to be called nitrous acid, and this one's called nitric acid. You probably have heard of nitric acid. Okay, so here, what is it? What's the rules? What kind of rule am I following here? So what it is going to be the root of the anion. Okay, now that's this guy. Now again, this guy here is nitrite, and this guy here is nitrate. Okay, so the root of the anion, and then we're either going to use as a suffix "aus" or we're going to use "ic." And "aus" would be the ite version, and "ic" would be the ate version. Sometimes someone might say "icky" if you ate it. So that's and then you just put plus acid on the end. And that is what we're looking at here for our main rule. And you notice this guy here has got 3 H's on it, which is no big deal. These are the H's that we can give away, but let's give this thing a name. So it's the root. This is phosphate. Okay, so now you just wrote phosp, and that'd be fine. People would know what you're talking about. People typically, well, I'll show them more common, like phosphor would be the most common root, phosphor. But if you wrote phos, that'd be fine. People figured it out. Okay, and then it'd be phosphor, and because this is phosphate, I'm going to use the ic version. So phosphoric acid. Lots of times these oxyacids, people are using them for their redox abilities. So you might notice that some of the 8 versions, or the ic versions here, are probably the ones you've heard of more often than the ite versions. You just don't hear much about phosphorus acid or nitrous acid. We use them because they do this oxidation very well, and therefore, that's what we've heard of. All right, let's jump over to the next one, which is going to be, how do I give a non-oxy a name? Okay, so a non-oxy is just going to follow this pattern NH, X, and this guy here, again, it just doesn't contain oxygen. But the most common example of these things are just simple anions, simple non-polyatomic, just a monatomic. Okay, and right here is the ones that are the most common. I would say right around here, right there. These guys. Again, we would not include oxygen because that would be water. We'll see that in a moment as we move along here. But in this case, let's just say, for example, HCl. Okay, now HCl, and all of these, you can always put water in there. So we know this, hopefully you know this is hydrochloric acid. Okay. So in this case, what's my format I'm following? Okay, well, always starts with hydro, and then you're going to put in the root of the anion, which is chlor, and then you always end in ic. Doesn't change here. And then acid. Okay. Another example might be, let's say, HCN, for example. We just mentioned that one earlier. Now this is one of the rare polyatomics. So this guy is cyanide. Okay. So what I do, I go hydro. My root is cyan, and I'm going to use ic, hydrocyanic acid. And that's my name of this guy. All right, so let's just practice a little bit. Okay, now again, I can go from formula to a name, but I also want to go from a name back to a formula. So here's a couple of examples of how we might do this with the name. Now, one thing you want to be aware of is, okay, one, you recognize this as an acid because it has acid in the name. But I'm going to start out with my main template, just kind of like that. All of these guys are going to start with an H out front. And I have a couple of different versions here so that we can, practice a few, 4 of them. And the last one, how many H's do we have? We might notice that sometimes we have more than one H. That's pretty simple. I'll show you. So hydro. Now again, when I see hydro up front, I need to know that I'm working with a non-oxy acid. So, and that means it's just bromine. It's not bromate. Okay, so bromate would be BrO3. Bromite would be BrO2. But bromide is just Br minus. That's the one we're looking for here. That's just going to be Br minus. It's -1. This is +1. And like ionic compounds, we charge balance. So this thing is just HBr, and it's an aqueous. All right, this is an acetic acid. Should look or sound familiar? Because acetic acid is vinegar. Probably could be thought of as maybe the most highly produced and consumed chemical in the world, maybe. Okay. So it starts with an H, and it's, I like to do it this way, acetate. There's no hydro in the front, so this is an oxyacid. So it's going to be an 8 or an ite. So I just translate, that's acetate. So let's go ahead and look on your ion sheet. Many kids will have it out right now. So acetate is C2H3O2. It's a negative one. It's a positive one. So we're good to go here. Charge balance is good. And you can put a nucleus on there if you like. All right, sulfuric acid. Now again, there's no hydro, so it's an 8 or an ite, not an ine. So this is sulfuric acid. So go to your ion sheet, find sulfurate. That's going to be SO4 minus 2. Now, here's our first opportunity to charge balance. Just like ionic compounds, very simple. 2 goes right there. And this is just going to give us H2SO4, and we'll put it in water for good measure. Okay, hydrophosphoric acid. Now we just had phosphoric acid as an example earlier I used, but this is hydrophosphoric acid. This is not phosphate. It's not phosphite. It's phosphide, and that's just plain old P. P minus 3. It's a plus 1, and H3 water. And there we go. How do we know how many hydrogen atoms we have? Well, we charge balance. Okay. All right. Some class practice. Okay. Now your job here would be to have your ion sheet out and to practice a few of these. Pause the video, try a few, and then I'll give the answers. And you can run the video through and try them out as you go. I'm going to go relatively quickly through the answers. And then, all right, so pause the video. All right, here we go. Hydronitric acid, that's going to be HN, okay, plus 1 minus 3 equals H3N. This is bromate, so it's going to be bromic acid. Now again, as I go through these things, I'm automatically going through a bit of a pathway in my brain, thinking about things. First pathway is oxyacid. So move oxyacid method. I go, okay, what is my formula for this? So I go to my mental or my note card to get the template that I'm going to follow to do this name. Okay? And therefore that's bromate, and I got bromic. All right, so this one here we just had a second ago, hydrocyanic acid. Dichromic acid, so that's dichromate. Go to your ion sheet, find it. It starts with an H, and dichromate is Cr2O7. It's minus 2 charge, plus 1, so 2 goes there. All right, this one here. Okay, this one on this side is not, it's not an acid. So this one's just going to be called, all right, good practice here. This is ionic, metal, nonmetal, never gives quantities. We're going to use a lot of these guys in our class for this chapter, so we want to brush up on that a little bit. Ionic, it'd be aluminum. Okay, chloride. All right, nonmetal, and therefore it's using covalent rules. Carbon, tetra, chloride. All right, copper 2 nitrate. So it's a metal polyatomic anion. This thing is ionic. So it's going to be copper with a positive 2 charge. That's that right there. Never gives quantities, just names. That's the name of that thing. Nitrate, NO3 minus 1. Charge balance, parentheses, 2. Sulfur, and 2 oxygens. This is using prefixes. Away we go. All right. And that looks like the end of our presentation. Thank you very much. Move on to the workbook. There's a couple practice pages that you need to do to become an expert at this so you can function easily through this chapter. Thank you.